Okay, in this video I'd like to take you through the electricity part of the GCSE physics for both triple and for combined science. So I'm going to look at just the electricity section of the specification, and I've got some notes which I'll try and hopefully help guide you through what it is that you need to know. So, just checking we're recording properly. Yes, we are. Okay. So, first of all, if you look at the specification, there's a couple of things that you need to just learn, okay, and that is the circuit symbols. Now, a lot of these, hopefully, you'll already know, but there's a couple of ones that will be less familiar with you, okay? So, fuse is sometimes confused with resistor, okay, because they've got very, very similar circuit diagrams. But chances are you'll already know switch, open and closed, a lamp, cell, a battery, which is more than one cell working together, voltmeter, which is just the V in the middle of a circle, and ammeter, A in the middle, so the meters, the V and the A, they're pretty straightforward. Ammeter is used for measuring current, okay, and voltmeter for voltage or potential difference. We've got a diode, which is a little bit different to a light emitting diode, similar, but it works similarly, but light emitting diode has one crucial difference. It gives off light. The resistors then, we've got the thermistor, which I always think looks like it's got an ice hockey stick running through it. And a variable resistor, which is a resistor, and funnily enough, you can change its resistance. So this is just a fixed resistor. Okay, so this is fixed. So once you know resistor, then variable resistor and thermistor are fairly easy. The light-dependent resistor, okay, these little arrows coming in represent light. Okay, and when you know that, then light-dependent resistor makes sense. And then when you look at the direction of these, the light is being given off, okay, and so it distinguishes an LED from a normal diode. So learn those, okay, look at them in a specification, or pause the video, look at them here, maybe make flashcards, learn those so as you know what you're doing and you can draw circuit diagrams. So you need to know those, you should be able to draw them, and you should be able to use them in a circuit diagram. Now, for electric charge to flow, so for you to have an electrical current in a circuit, you need a source of potential difference. So I want you to think about a ball on a hill. Okay, so it's the potential gradient, the gravitational potential gradient that would make a ball roll down a hill. And so there's a potential difference there. But in terms of an electrical potential difference, we call that a voltage. So if you had a negative charge, it would move from negative to positive. It would roll down the hill, okay? And you can think of that in the exact same way as a ball rolling down a hill, or you can think of the negative charges being attracted towards the positive. A positive charge would go from positive to negative, okay? So it's the potential difference that's making those charges move. Those charges moving then represent a current. Okay, so a current is a flow of electrical charge. Okay, and you need to know the equation. Okay, so you should be able to recall that. Okay, and then a current will have the same value at any point in a single closed loop. And what I sometimes like people to think about is what's actually known as Kirchhoff's law, which is that the current flowing into a point is equal to the current flowing out. Okay, so if I say that I've got 2 amps and 3 amps flowing into a point, and 1 amp coming out, then I have an unknown current here, okay, and that's just, in total I've got 5 amps going in, so I've got to have 5 amps coming out, and that's down to something called charge conservation, that those charges can't just magically disappear. and so we've got a current of 5 amps in total. If I take away that 1 amp, then I find that I've got 4 amps here, okay, in this branch of the circuit. So, the idea of current in equals current out is quite useful, and you can apply it to a parallel circuit where you might have 4 amps in, 1 amp going down one branch of a circuit, and then you say, well, what's the other one? So as I've just rubbed it out, it's 3 amps. Okay, 4 amps in, 4 amps out. Have to be split evenly, and in a lot of parallel circuits it won't necessarily be split evenly. Okay, so we know that we need a potential difference for current to flow, and we know that current is charge flow divided by time. It's the rate of charge flow. So we can turn this into this little equation, and we need to remember that, okay, because it's one of those equations that we need to recall. Okay, so what links that potential difference with the current is resistance. So this is Ohm's law. Potential difference is current multiplied by resistance. Okay, so for any circuit there will be a resistance, which is a property of the circuit, and there will be a potential difference across to make the current flow, and there will be a current flowing. Now, this formula, V equals IR, this is an incredibly important formula for electricity, and again, you need to be able to remember it. You need to be able to use it. So V equals IR, where V is your potential difference, also known as voltage sometimes, and that's equal to current multiplied by resistance. So if you're a fan of the triangles, okay, then just remember then that the V is going to go on top because the I multiplied by the R, they're going to go in the bottom. Now, I'm going to apply it to this situation here, okay. If I've got a resistance, if I know the resistance, then I can work out the total current. If I know the current, I can work out the resistance. And the idea that the voltage applied by this 3 volts here is going to be the voltage across the component, provided that the wires have basically no resistance. Now, all of the application of electricity basically comes down to the V equals IR ideas. So you need to, in terms of practical skills, have been able to have done things with circuits, either on simulators or in reality. Okay, and because the resistance is a property of a circuit, and because of some really, really good sort of physics ideas, you're often asked to look at the resistance of electrical circuits. So to look at the resistance, okay, you need to know voltage and current. And this is why it's a really, really good little practical. You can't measure resistance directly, okay, so you need to measure voltage and you need to measure current. And in doing so, then you can calculate the resistance. Now, you can get little machines that can be set to measure resistance, but what they're doing is they're measuring a voltage and a current and then calculating them all inside and then just telling you what the resistance is. So, if you look at the length of a wire at a constant temperature, okay, a wire at constant temperature will have a constant resistance, okay, but there are factors that affect resistance, like temperature. If you heat a wire up, the atoms vibrate more, and that means that those atoms get in the way of the electrons more, so the resistance increases. So when you're doing your measurements, you would need to have your voltmeter in parallel, because that's how they work, and your ammeter in series. And if I just look at a wire here, Okay, if you wanted to measure the resistance of a wire, you would just use some crocodile clips, okay, and you could put a little wire in those crocodile clips, and you'd measure the voltage across the wire and the current through the circuit, okay, with this sort of setup, and you would have then the ability to work out the resistance. But in having this little wire here, you know, it does have its own basic resistance, so you can think of it just as a resistor. Okay, and the factors that will affect its resistance are its length. If it's longer, the current has to go further, which is harder, which means there's more resistance. A thicker wire will have a lower resistance because the electrons can all spread out and go nice and slowly through the wire, which requires less energy on their part, so lower resistance. And then the material of the wire, with obviously the good conductors like copper, gold and aluminium having a really low resistance or low resistivity, and then different materials that aren't good conductors having a higher resistance. Okay, so low resistance, hopefully I just said that right, low resistance or low resistivity, copper, aluminium, gold, and then we often use an alloy called nichrome, which has got a higher resistance for measuring the resistance of a wire. Now, in terms of your practical kit, yes, you need a wire, you need your voltmeter, your ammeter, and some sort of power source, so either a power supply or some batteries, but you also need your crocodile clips as well. Now, you can measure the thickness of a wire with a micrometer or vernier calipers. So both of those are really good for measuring thin objects, okay, and measuring thicknesses. So if you wanted to accurately measure the thickness of a pencil or a hair or a wire, you could use either a micrometer or vernier calipers. And it's well worth Googling those just to see what they look like, so as it makes a little bit of sense. Now, I'm going to look a little bit at parallel resistors. It is incredibly complicated, what I'm about to go through here. So bear with, okay? Maybe this is more applicable to higher tier than foundation tier. There is a formula for looking at the total resistance. It's just not one that you need to know, so I'm not going to go into it. But if we're looking at the resistance in total, then we need to look at the total current and the total voltage. Now, in this particular situation, I've got my 3-volt battery, and I've got a set of resistors. So the current through each resistor is equal to V over R, and this is just Ohm's law rearranged. So my voltage was 3 volts, and I said that the resistance of the first resistor is just going to be R1. Then in the second resistor, R2, I've got current 3 volts over whatever R2's resistance is. And then the total current is going to be 3 volts divided by R1 plus 3 volts divided by R2. And then if I've got more resistance, then I'm going to have more and more current. Okay, so I total will increase. So by adding these resistors in parallel, I end up with more current. So adding resistors in parallel will increase the current. Okay, because what's happening is it's giving additional paths for the current to go through. Okay, it could go through R1 and R2 and R3 if you put a third resistor, and R4, and you can keep on adding these resistors in parallel, and that will keep on increasing the current. Okay, so the total current will increase. Okay, so the total current will be bigger than it is through each individual resistor. So the total resistance is smaller than the resistance of each individual resistor. Okay, so that's one of the parallel rules if you're doing triple, that your total resistance, if you've got parallel resistors, is less than if you look at the individual resistors. Okay, so for example, I've got two 2 ohm resistors here, and I'm going to calculate the current through both of them. Okay, so the current through both of them, I, is V over R. My voltage was 3 volts. Okay, and they were 2 ohm resistors, so I get 3 volts divided by 2, which gives me 1.5 amps for my current. So in one of them I've got 1.5 amps, and in the other one I've got another 1.5 amps, and in total that gives me 3 amps. Okay, so if I want to work out the overall total resistance for both resistors combined, then I've got my 3 volts as my supply voltage divided by my total current, which is 3 amps, and then that gives me 3 over 3, just 1 ohm for a total resistance. So this is just for parallel resistors, and that is just for triple students. Okay, so if you're a combined student and you're thinking, I don't get it, that's fine, not a problem. So moving back into what is relevant to lots and lots of people, everyone technically, is looking at Ohm's law. I keep on talking about Ohm's law. So Ohm was the person who said, right, I shall look at resistance, and I shall look at current, and I shall look at voltage. And he discovered basically, as you increase potential difference, you increase current, and that they are directly proportional to each other. So that means, because they're directly proportional to each other, okay, that you get a straight line through the origin. Now, the current through an ohmic conductor, okay, if it's ohmic, it obeys Ohm's law, okay, and if it obeys Ohm's law, then it has a constant resistance, okay, and so you'd get a graph like that of it, okay. Now, in this particular case, it's not as easy as it could be mathematically, because potential difference is the thing that you vary, so it's your independent variable, and independent variables get plotted on the x-axis. And on the y-axis is the dependent variable. Okay, so as you change potential difference, that affects the current, you measure the current. Now, what that means, okay, and this is pushing possibly into higher tier. If we look at the gradient here, the gradient of this line, if we think about y equals mx plus c, okay, then you have, let me just squeeze this in, I'm going to put this in up here. Well, I know the equation of a line is y equals mx plus c, but we don't need to worry about the plus c because there is no y-intercept, it goes straight through the origin. So we have y equals mx, okay, now our y is current, which is I, and on our x-axis we've got v, okay. Now if I wanted to say I is equal to something v, that something is, of course, the gradient, m, and the gradient in this case is, because I is equal to v over r, okay, we can say, well, v is the x part, okay, so I is some constant multiplied by v, Okay, I can put that as M, and that is 1 over R, so M is 1 over R. Okay, so I could just put this equation here, I is V over R, as I is equal to 1 over R times pi V. And then it makes it look a little bit more like y equals mx plus c, but in writing it like that, we've just discovered that m is 1 over r. So the gradient of this line, okay, is 1 over the resistance. Anyway, that math's relevant to higher tier, not relevant to foundation, but what I'm about to say about looking at components very much is relevant to all groups. So if you want to look at the resistance of a component, you need to change, or how it changes with voltage. You need to change the voltage, measure the current, and then you can look at how the resistance is changing. Okay, so to change a voltage, what we do is we put a variable resistor in series with the component that we're looking at. We can then measure the voltage across that component, and we can measure the current through the component. Now, what we've got then, when we look on a graph, okay, is either we've got the sort of graph that we'd expect for a diode, or for a lamp, or for any other component. Okay, so we change the voltage, we measure the current, and then we'll get some values, and we can plot those, and they give us an indication about what's happening with the resistance. Okay, so the variable resistor will change the total resistance, which changes the current, and it changes the potential difference that is available for that component. So in changing this here, we're going to end up changing the voltage here. Okay, and that's something that it's really good to get your hands on the practical equipment to do so, but there hasn't been much practical application or much practical work for students this year because of COVID, so you're just going to kind of have to believe that what I'm saying is true. You change the value of the value of the resistance of the variable resistor, and it will affect the voltage of the component next to it. Okay, because basically, if this has now got a big resistance, it's going to hog the voltage from the power supply. Now, when you're measuring a current and a voltage, you're going to take a measurement, and maybe you start off with 0 volts. Okay, and you'll have a current. Then you change the voltage by changing the resistance of the variable resistor, and you now get 1 volt. Okay, and you've now got another value for current. Okay, so we end up with the current at the voltage 0, current when the voltage is 1, current when the voltage is 2. Okay, and we go up and up and up and up and up, and we end up with a set of results for a voltage and a current that are either a nice straight line for a resistor, or they do something like that if it's a filament lamp, or they do something like this if it's a diode. But we haven't got any negative voltages to look at what happens to the current when the voltages are negative. So what you'd need to do is, if you've got a battery, you can swap the battery around, just turn the battery around, okay, and then you could try -1 and -2, -3, okay, and that will allow you to get these negative voltages, okay, that for a diode would give you a nice flat line, okay, because the diode will only conduct when the voltage is positive across it. And if it was for a filament lamp, it's doing something like that, okay, well, it's symmetrical, okay, so it would do the same thing but opposite for negative voltages. and if it was a resistor with a nice constant value for resistance, then it'll give you a straight line through the origin. Okay. Now, if we look at these graphs, okay, you need to measure the resistance of components such as lamps, diodes, and thermistors. Okay. Now, for a filament lamp, as you increase the current through it, it starts to get hot. As it gets hot, the resistance will increase, which makes it more difficult for more current to flow through. And so you kind of start to get to the point where there's almost a maximum current that can go through. You're making it more and more difficult to get more current going through. So the current will slowly rise, but not as quickly as it did initially. Okay? With a diode, you have a very high resistance in one direction, and the resistance decreases then as you get this positive voltage above a certain point. It goes, oh, okay, I'll be a conductor, okay, and it starts to conduct, and the current will increase very rapidly at that point then. So you can think of this as like a switch on voltage. Other components that you look at, okay, we look at thermistors. And we look at light-dependent resistors, LDRs. And as you increase the temperature, or as you increase the light intensity, the resistance of those falls. And that's because they're made of something called semiconductor, which kind of wants to conduct, but only if you give it a little bit of extra energy. So that energy could be thermal energy, or it could be light energy. So with a little bit of extra energy, they conduct a little bit better. Okay. And then those are described here in the specification. Okay, so your resistance of a thermistor decreases as the temperature increases. And you might use that for like a thermostat at home for controlling your heating. Okay, you have something like this setup here, where you might have a thermistor, and the voltage across it will vary depending on its resistance. You put it in a circuit like a potential divider, which is what this is. And then because the resistance will vary with temperature, then the voltage will vary with temperature, okay? Because as the resistance here is high, it gets a bigger share of the voltage. It will get a high voltage or higher voltage, and that can then be used to control some sort of switch. So that's quite useful. And you could do the same thing with a light-dependent resistor if you wanted to control something that changed with light. Okay, so like a security light that will only come on in the dark, or that sort of situation. You would use something like a light-dependent resistor as a light sensor in a laptop or a mobile phone that just changes the brightness of your screen automatically. Okay, so if you think, how does that work? Well, it's with an LDR. Okay, so it just goes, oh, the voltage has changed because the light has changed. Oh, you better make the screen a bit brighter. So thinking about the thermistor, the voltage varies with temperature. Thinking about the LDR, the voltage, if it's in a potential divider, will vary with light intensity. Now, if you're looking at resistance of either of those, then you would use a voltmeter and an ammeter to measure the voltage and the current. the voltmeter again in parallel, the ammeter in series, and look at the resistance then and how it changes with light intensity. So you could keep a nice constant voltage and change the light intensity and the current will change. Or if it's for the thermistor, you could change the temperature and the current will change. And then your values of voltage and current can lead you to a resistance, again by using V equals IR. Now this required practical for filament lamp and a diode and a resistor at constant temperature is what I explained up here with the crazy complicated drawing. You use a variable resistor to vary the voltage across the component, and then it changes the voltage, changes the current, and then you can measure the resistance by combining those values. So next up then is a series and parallel circuit. So series and parallel circuit, there's rules. Okay, so for any student who's studying triple award, you need to know the series and the parallel rules. But with combined science, you only need to know the series rules, but you kind of also need to know some facts that go with the parallel. So you may as well actually just learn the parallel rules. So we've got series and parallel, and I've highlighted the rules here. And best bet, just learn them. Okay, learn the rules. It'd be good to understand them. Current the same through each component. Well, in series, that's because the current can't go elsewhere. Okay, there's only one loop in series, so the current stays constant. It has to be the same through each component. The total potential difference of the power supply is shared between the components, because if you've got something like, if I just go with 2 resistors in a circuit with a battery, okay, the current will go through both of these. Okay, and what's making the current move is the potential difference. So if I go back to the analogy that I used right at the start, where I've got positive and I've got negative and I've got my gradient, if you think about the charges moving, okay, well, through the resistor, this is the first resistor and this is the second resistor. Okay, so the total drop is like both resistors combined. Okay, but when you add extra resistors, if I say this is 2 ohms and this is 3 ohms, okay, in series the total resistance is just going to be 5 ohms. Okay, now the simplest sort of problem that you can solve again goes back to V equals IR. If I said that the voltage here was 3 volts, it's a battery, not just a single cell, and I said what is the current? Okay, well I is V over R. So I say, right, in total we've got 3 over 5, which is 0.6, and that's for a current. So the unit is the amp. Okay, so we've got 0.6 amps. So that is your current in a circuit. Okay, or if you had a current and a resistance, then you could do V. You could find the value for V by just multiplying the two of them together. Okay, so that's your basics of P4. Okay, I think P5 is shorter to look at, so I'm going to quickly look at P5 before the end of the video. Okay, but feel free to go back and look at any of those sections again. Some of it was quite mathsy, so I apologise for that. Yeah, here's the next little sections. So we've got here the parallel rules. Okay, so your parallel rules, these are pretty useful. Okay, so potential difference across each component is the same. And apologies for what I said just now, because it's down here that your P5 starts. Okay, so that's P5 if you're referring to textbook chapters, okay, in the main textbook. So we've got this R total, this bit here. This goes back with the P4 section. Where is it? Right at the bottom. Okay. So this, in the specification, the next page is what I've got here. So R1 plus R2 is equal to R total. That's what I just did here. Okay. Using that here. So anyway, I was talking about the parallel rules. So the parallel rules are here. Okay. So potential difference across each component is the same. And if I just draw a tiny little parallel circuit, again, I'm going to use a battery with 3 volts. I'm going to do a 2 ohm resistor, and I'm going to do a 3 ohm resistor, because those are the ones that I used in the series example. The potential difference across both resistors is the same. So the potential difference across both of them is 3 volts and 3 volts, okay? Because each of the charges getting from one side to another gets the same. So if we use the hill analogy, you've got positive, you've got negative, okay? So that's one route, okay? And then the other route is just alongside. So it's like two things rolling down a hill side by side, as opposed to one after another. Okay, so still the same start and finish point. Okay, still the same difference in potential. So the total current through the whole circuit is the sum, because of that idea that your current can split. Okay, so we've got a current coming in, and that's the total current, and it'll split up into this current here, which I'm going to call I1. Believe it or not, that is a 1, and then this one here is I2. So the total current is equal to the first current and the second current. So first branch and second branch added together. And I could work out that I1 is V over R from that lovely equation that you might be thinking I'm obsessed with. It is my favourite equation. Everybody should have a favourite equation, especially if you're a top nerd, which I claim to be. So 3 volts over 3 ohms. Oh my god, 3 divided by 3, I can do that in my head. It's just 1. So 1 amp. And then the second current, I2, I've just written a 3. I2 is, again, V over R. Okay, so 3 volts still over... Oh no, I got this backwards. My bad. And I'm doing this in one take as well, which means that I'm not going to delete that mistake. Maybe one day I'll edit it out. 3 ohms. Right, so top one was 2 ohms, bottom one was 3 ohms. And that means that my top current is different. So my 3 volts over 2 ohms is 3 divided by 2, 1.5 amps. And in the bottom, 3 divided by 3 is still 1.0. Okay, so that gives me a total of 1.5 plus 1.0, which is equal to 2.5. Okay, amps. So, where was I? The final rule then is that the resistance of two resistors is less than the resistance of the smallest individual resistor. Okay, so let's just check that. So I can actually do some more sums, because I love it. Now, you're probably thinking, I wonder what equation he's going to use. And the answer to that is my favourite equation. R is equal to V over I. So I've just rearranged it to suit me here. So I'm going to use the total voltage and the total current. So the total current was 2.5. Okay, so I've got my 3 divided by 2.5. Now, I've left my calculator about 10 feet away, and I can't really be bothered to move. So, if I do 3 divided by 2.5, that's the same as saying 12 divided by 10, which I can do, which is 1.2 ohms. Oh my god, what was that rule? The total resistance of the two resistors is less than the resistance of the smallest individual resistor. It is true. It is true. 1.2 ohms is less than 2 ohms. Yeah. So, it didn't lie. So yeah, basically, if you add resistors in parallel, the total resistance gets less. I said that earlier there. Right. I have definitely drawn enough series and parallel circuits for you to make you want to never see another circuit again. But just in case you want to see another circuit again, there we go, look. That's another circuit. Okay. So, I'm going to move on to your domestic electricity. So DC and AC, what's the difference? Well, DC stands for direct current, and AC stands for alternating current. So direct current is just where you get your current going in a constant flow, okay? So it's constantly going from one direction to the other. So one side in one direction, one place to another, okay? So if you think about the current, we talk about current as being positive, so it's just going from positive to negative. If you're thinking about the electrons, because you're crazy clever, then you're going to be thinking, well, the electrons are also always going in the same direction. It's just from negative to positive. So the electrons actually flow in the opposite direction to current, because about 150 years ago, people didn't realize that the current was caused typically by negative electrons. So they modeled everything as positive. But anyway, an alternating potential difference goes positive, negative, positive, negative, positive, negative. So when you look at it, it looks a little bit like a wave. So the voltage or the current would be going positive and negative. It would be getting bigger and smaller, bigger and smaller. So it has constantly changing values, and it's constantly changing direction. So when you look at mains electric, okay, the sort of average voltage, or the voltage that we say it has, is 230 volts, okay, so it acts like it's 230 volts DC equivalent, and the frequency is 50 hertz, which means it does 50 oscillations every second, okay, so it goes positive and negative 50 times in a second. Now, we use alternating current because you can put it through a transformer. And when you put alternating current through a transformer, you end up with the ability to increase the current, or you can increase the voltage. Okay, so because power is current times voltage, you cannot increase both of them together. Because you have a constant power, if the current goes up, the power has to go down. Sorry, if the current has to go up, the voltage has to come down. And if the voltage goes up, the current comes down. So that means that the power will stay constant. Now, transformers are really, really useful with alternating current because they can increase and decrease the current and the voltage. So if you reduce the current, that has the benefit of reducing the heating effect, which in turn means that you might waste less energy. if you reduce the current, you increase the voltage. Okay, so like this option here. Increasing the voltage makes it more dangerous. So for example, in power lines, you don't want heating. So although they have quite large currents in those big power lines, they have quite a big current and a ridiculously high voltage. Okay, crazy high voltages. Now those crazy high voltages are very dangerous. So the power lines are very high, so you can't touch them even by accident. Whereas around the home, okay, and when you bring electricity into people's homes, you reduce the potential difference, which makes it more safe. But in doing so, you'll increase the current, so it makes it less efficient. So you do that only like when you get close to a person's house. So compared to the distance from like the socket in your home to somewhere where there's a transformer, it really isn't going to be that far. Okay, it might be like a few hundred meters or something, compared to high voltage power lines that might run for hundreds or thousands of miles or kilometers. Okay, so yes, it's less efficient to use low voltages, but they're not going that far, so that's okay. Now, just checking. Yes, I'm still recording. Good. With mains electricity, okay, around the home, we use cables that are insulated, so as you don't get electric shocks, and the insulation is covered with a colour code. So the colour code is live, is brown, okay, that's a nice easy way to remember that. If you touch it, it's the same colour that your pants will turn. The neutral is blue. A way that you could remember that is it's a nice neutral colour. And then the earth wire, which is for safety, is connected to the metal casing inside a metal appliance, and that's a yellow and green. So the neutral wire will basically be at 0 volts, and the live wire will carry this alternating positive, negative current and potential difference. Okay, so this part of the specification just kind of describes that a little bit. Okay, now we've got obviously the safety of in sockets we have a switch, but a live wire may be dangerous even when a switch in the main circuit is open, just because you might basically use your own body as a short circuit switch. So if you were to touch a live wire, you might get yourself a nice little electric shock because you're providing some sort of complete circuit. So electrons, when they're at a higher energy, so some higher potential difference, they just want to relax, chill out, spread out. Okay, so as they spread out, that's a lower energy state for them to be because they all repel each other. And so in the ground or the earth, they can physically spread out. And that's a nice low energy state for them to be in. So they always want to go to this low energy state, and we call that the ground state. And it can literally mean that they're in the ground. And that's what the earth wire is it takes electrons into the ground so they can spread out if there's a fault. Now you also need to do calculations, okay, for this part of the electricity course, and the main one to look at is power. Okay, so electrical power, which I showed the equation higher up on my notes here, is P is equal to VI. I always remember it's P equals to IV. I don't know why, that just works better for my head. But because we've got the other equation, the one that I say is my favourite equation, V equals IR, we could swap in IR in instead of V in this part of the equation, and then we'd have IIR. And so your exam board loves that particular equation, P is equal to I squared R, because it does a really good job of explaining some things. If you set this as your equation for power, for electrical power, then you only need to know the resistance of the cable or the resistance of the device and then the current through it, and it explains why you would want national grid to have a low current, for example. So if you've got a low current in the national grid, then you've got low power being less power being wasted in those national grid cables. Okay, so if we reduce the current by a factor of 10, then you reduce the power lost by a factor of 100, because 10 squared is 100. Okay, you also want a nice low resistance in cables. Low resistance in cables will also decrease the power lost in those cables. So this is me just putting P equals IV and V equals IR together to make the IIR, which is equal to I squared R. So if you think about some power cables, okay, they've got a low resistance, which is good, because that means that there's less power loss there. But then, like I said, reducing the current will reduce I squared. So reducing the current by 10 reduces the power loss by 10 squared, so 100. And where have I got my other little section? Where was it? There we go. So this, I'm thinking about like an appliance. The cables to an appliance have a low resistance, and then the appliance itself will have a bigger resistance, okay, and that is where the power is being used. So if you've got a small resistance in the cables, there's not much power used in the cables, so there's not much heat in the cables. But something like an iron or a kettle, where you want the actual energy to be used and transferred, it's got a bigger resistance, and that's where the potential difference will be used up, and that's where the power will be used up. Okay, so the power is transferred in the device rather than in the cables. Okay. If we then look at the basic idea from energy, the energy transferred is power times time. Then we can use that in terms of electrical energy. But then we've also got this other formula, which is the formula that kind of defines what a volt is. Okay, so a lot of people are aware that voltage is linked to energy transfers, and that's why big voltages lead to big energy transfers, but they don't necessarily fully understand why. And so if you look at energy divided by charge being equal to potential difference, we say that a volt is a joule per coulomb. Okay, so 1 volt is 1 joule per coulomb. That is really, really messy writing, and I apologise for that. I need to put my tablet a bit more flat again. So yeah, 1 volt is 1 joule per coulomb, and that's the definition of what a volt is. It's the energy per charge. Go away, little text box. We don't need you right now. It thinks it does need it. It doesn't. Okay. Anyway, whilst I talk to my computer, let's think about yeah, that's it really for that actually. There isn't much else that you can do. If you're particularly smart, then you can actually take this V is equal to E over Q. And if you said, right, let's multiply it by I, Now let me think, what's the formula for I? Current is Q over T. So if I do I multiplied by V, or V multiplied by I, okay, then I end up with just E over T, because those two Q's will cancel, and that obviously is power. Okay, so that definition of electrical energy being charge multiplied by voltage, you can rearrange to give you voltage as energy over charge, and then you can see how current times by voltage gives you electrical power, because the two things will basically end up with just energy over time. When you multiply them, you're left with energy over time, which is power. The other thing then is looking at fuses. Okay, so you should be able to explain how the power of a circuit device is related to the potential difference and the current, so P equals IV, or you could look at the energy over time is also equal to power. And if anything was particularly nasty, either in your upcoming exams or future exams, you might have to equate those two. So you could have energy over time is equal to current multiplied by voltage. That could be fun or not. So anyway, national grid, talked a little bit about the national grid. Okay, the national grid is just cables and transformers that link the power stations to the people who want the power. Okay, because otherwise, if you didn't have that, then we would need to have little generators. Everybody's house would need a little generator. So we need a national grid because it's just an efficient way of doing things. Now then, looking at power, if you'd say power is current multiplied by voltage, then you can say, well, power divided by voltage is current. And if you've got a known voltage, like the voltage of mains electricity, 230 volts, then you can work out the fuse required, or the current that will flow in a circuit, and therefore the fuse that will be required for a particular appliance. Okay, so fuses come usually in three values: 3 amps, 5 amps, and 13 amps. Those are the ones that we use kind of in our normal domestic appliances. Other fuses are available, but not necessarily for GCSE calculation. So they keep it simple. They usually use just those three. That bit I've done with you. What else have we got? Electrical power transferred to consumers in the national grid. We've got step-up transformers increase the potential. Step-down transformers decrease the potential difference. That's fairly straightforward. For triple physics only, we've got static electricity, which is fairly straightforward. Okay, so static electricity is electricity where you have charged insulators. Anything that's insulated, you can't get a moving charge. You can't get a current because it's an insulator. And so static is caused by, either a transfer of electricity by friction, or potentially just a lot of energy jumping, like a spark. So you can't transfer protons because they're deep within a nucleus. So you can't build up positive charge by transferring of protons. Static electricity works by transferring electrons. And those electrons are negative, so if something ends up negative, it's because it's got extra electrons, and if something ends up positive, it's because it's lost some electrons. So your attraction and repulsion is a non-contact force, which means it operates over a distance. It don't have to be in contact like a push or a pull. And that's fairly straightforward. And then there's a little bit on electric fields as well. So for a charged sphere, if you took any sphere, we talk about electric fields as being the force experienced by a positive charge. So if I've got a positive sphere, then I put a positive charge here, just like a sample positive charge, and said, oh, what happens to it? Well, the force acting on it will be repulsive, so it will be repelled away from the sphere. So we draw field lines as being away from the positive charge. That box is really annoying me now. It's quite difficult to not just swear at it just a little bit. What was I saying? So field lines show lines of force. Where the lines are close together, there's basically more force. Where the lines are further apart, there's less force. And so, if you've got a negative charge here, we go whoop, whoop, whoop. Any positive charge would be attracted inwards, so the lines of force are inwards, and the lines show the direction as well as the amount. So very little force here, and more force here. More force as you get closer, so the force goes from little to big. And let's just take you out of tablet mode because you are annoying. Okay, so when we then look at the idea of what electric field is, it's just an area. A field is an area. When we talk about a force field, it's an area where you'll experience a force. So the concept of an electric field is an area where there will be an electrostatic force. Electrostatic force just means a force on a charged object. Okay, and so we use positive charges just because we need a reference. To use positive or negative, use positive. Okay, so positive is the convention that's used. So we show lines of force on a positive charge. Basic ideas in terms of transfer of charge, electric shocks, that sort of idea. Charge, if you've got a built-up charge, it's kind of got some energy, it's got some potential energy, and you can reduce that potential by allowing the charges to get spaced out. So if I were to connect a ground wire, okay, so I'm going to connect a wire, or if I connected a wire here to Earth, so I'm going to use the symbol for Earth, which is those lines. Any electrons, any excess electrons would flow out of that charged sphere into the Earth, and any electrons could flow from the Earth into the charged sphere here to cancel out those charges. And that's basically, if anybody who's doing computer science is still listening, how the Earth cable or the Earth wire on a appliance works. Okay, it just allows movement of electrons from the Earth into a device if there's a problem, and the casing becomes charged. So that people don't get electric shock, the Earth wire carries any charge. And in fact, with an Earth wire, because it's a really low resistance wire, if you have anything flowing through the earth wire, any current flowing through the earth wire, if there's an electrical fault, you get a really large current flowing through that wire, but that large current will then blow the fuse in the device, and in blowing the fuse, it switches off the device. Which means that the device is no longer live, so it really is actually quite clever that an earth wire also, in using the earth wire, keeps the user safe, but also allows the device to turn itself off. So anyway, I can hear people coming around school now to kick me out. So I'm going to stop recording videos now and leave that there. I hope the video is slightly useful and we'll kind of review some basics. Apologies for the amount of maths earlier on in the P4 section, but you know, it is the reason why most people hate electricity as a GCSE topic. Yeah, that's covered. Oh, there we go. Here's my little safety thing of the live wire. Safe earth wire connected to metal casing and a person allowing electrons to flow into the ground. So live wire does that rather than allowing those electrons to go through a person to the ground. Yeah, hopefully the video has been useful. If I get the opportunity and time and energy, then I will try and record another video for radioactivity and particle model. Okay, but if not, electricity is the one that people hate the most, and energy, which was the video I recorded earlier, is the one that people did earliest on in the year and are most likely to have forgotten. So other things are slightly fresher in your mind, hopefully. So good luck with any revision that you're doing at the minute, and if you're watching the video, you're actually doing slightly more revision than none, so well done to you just for that. Okay, so good job, have fun, and have a nice weekend.